So, before I dive into talking about the homeworks, does anyone have any concrete questions that they want to ask me about this past week? Nope. Okay, then I will start talking about uh, your second homework. So, I'm going to start off with question number 2. I think it's one of the more interesting ones here. So, uh, we have G is defined as 1x0, 1, with x being an integer on the collection of 2 by 2 matrices, upper triangular matrices, because that guy down there is a 0. So is G a group under the usual multiplication, under normal matrix multiplication? So what is the definition of a group? Someone give me the group axioms.
Must be close under the operation.
Yeah, so closed under star. What else? Sorry.
Associative.
What else?
Inverse.
And what does this basically assume? Inverse is meaningless without? Hmm? What is the last one?
Identity.
Identity.
Yes. Identity exists. And we can state these guys formally. There exists an E such that EA is equal to AE is equal to A for all A in G. And here you would have A inverse, or there exists an A inverse such that A inverse A is equal to A inverse is equal to E for all, for each A in G. So first, let's check number 4. Is there an identity element? Come on, guys. This isn't a hard one. Not x equals 1. Yes. X equals 0 gives us the identity. So if we set x equals 0, we get 1, 0, 0, 1, which any of you guys who have done any linear algebra should recognize as the identity matrix. Cool. So 4 works. Let's go up to number 1 here. So 1 x 0 1 times 1 y 0 1. So is this closed under multiplication? Benjamin, is this closed under multiplication? Ben Castle? No? Pedro, is this closed under multiplication?
I don't think so.
Okay. Somebody do this multiplication for me. Cool. Thank you, Marius. So we get this guy is going to be equal to 1, right? Top left is going to be equal to 1. This guy right here is x plus y. This guy right here is 0, and this guy right here is 1. Which, actually, this right here, that calculation should be enough to tell you that this is in fact a group. And in fact, this operates exactly like addition under the integers, right? If this guy, who we could think of as if the only thing that distinguishes this from any other element is this top right, so we could just think of this as x. So x times y just gives us x plus y in the integers. So we can basically think of this as just addition, but we should keep on checking, right? Yes, yes, it is isomorphic to the integers. So is this associative? Well, he actually said that you can assume that is associative, just because this is a subset of matrix multiplication, which we know is associative. So we don't actually have to bother with that. So check, check, check. And all we have to do is check that an inverse exists. So based off of this, what do we think the inverse is going to be? So if I have 1x 0 1, what do I think the inverse will be? Yes, exactly. That we would just sub in 1 0 negative x 1. Cool. So it fits all of our criterion for being a group. Therefore, it is a group. Does anyone have any questions about this one? Nope. Okay. We could also do basically the exact same thing for a lower triangular matrix, I think. And you could alter this in various ways to have something that's a little bit more general than this. Clear. People have a next question they want me to do?
Question 6.
6? Okay. Suppose G is a group with n elements and identity E. Let G be in G, show that there are positive integers.
I just used contradiction, but is there another way you could do it?
Yeah. If there's a finite number of, so the core insight here, which I don't think you guys have proven yet, but the core idea here is if G is, if big G is finite, then there has to exist an A such that G to the A is an A greater than 0, but is equal to the identity element. He's using epsilon, so I'll use epsilon. So why is this true? Just on an intuitive level. So there's only finitely many things that G to the A can hit, right? And we're not guaranteed that it'll hit every single element. There are cycles. So if I had Z5 cross Z7, so, and I had this doesn't hit every element. This only hits 5 of the 35 elements, but it has to cycle through at least by 35, right? So if that tells me that no matter what, if I raise G to the cardinality of G is going to be the identity, regardless of what G that I start off with. So if I just pick G, if I to the B plus the cardinality of G, then that is going to be set this guy equal to A. That will work. You have to do a little bit of work to show that no matter what, if I do the cardinality of G, I'll cycle back to the identity. But and that should be a pretty intuitive idea for you guys. Does that make sense? Is that somewhat intuitive for you? Bueller. Nope. Cool. So, which question should I look at next? Let me look at 5 next. Cool. Does Z7 be the equivalence class of? Okay, so I'll look at 7 and hopefully part C will be enlightened. So let Z7 be the set of equivalence classes. So it's mod 7 with both addition and multiplication, mod C18. So let A, so the determinant so 5A, if we look at the determinant of A, then we'll get that that is going to be equal to this guy times this guy minus this guy times this guy. So we get 1 times 1 plus 4 times 2, all mod 7, right? And you should be able to check to see, hey, this is in fact 0. You get 8 here. Sorry, this should be minus. The determinant gives you minus. So 1 minus 8 mod 7 is going to be equal to 0. You should be able to, that should make sense to you guys. Verify that this has an inverse in GL2Q. So I'm pretty sure that this guy is just saying that you should be able to find that it has the determinant. Sorry. Okay, so what is GL? You guys have talked about the general linear group. Come on, someone tell me what GL is. Have you guys talked about the general linear group in class? Okay, so yeah, the general linear group is the set of matrices that have determinant 1. So they are, in a sense, the matrices that preserve kind of size in a sense, right? So does this guy have an inverse in GL 2Q? Oh, sorry. They have a determinant with norm 1, right? So if we were to work in complex numbers, we would also allow anything on the unit circle. And then we also, just in regular integer or rationals and reals, we allow -1. So it's the idea that they have matrix with determinant 1 is the right general idea, but it's slightly more general than that. So is this, what is the determinant here? So determinant of this guy, that would be 1 minus 8. So that would not be in 7Q, right? Justin, you want to chime in here?
Since it's GL2Q, do we still do the mod 7 or not?
Well, the 2 is just saying it's a 2 by 2 matrix, I think, right?
Yeah, but like, you know how in part A it's for mod 7 and then there's mod 7, this one's in the rationals. So do we still so we don't take the mod 7 in part B, right?
Well, so in yeah, you shouldn't be doing mod 7 in part B. Are you sure that GL is not just the group of invertible matrices?
I don't know. That's one of the things that's confusing me about the problem.
Because those are 2 different sets of matrices that we're generally pretty interested in, and I could be getting those mixed up. Let me just.
When I went in the book, it said I think it said the ones with determinant.
So it's the set of invertible matrices. That is a separate, like that is also a group that we are interested in. The set of matrices with the set of matrices that have determinant 1 is another group that we are interested in. But apparently this one is the all invertible matrices. So okay.
I'm sorry. I thought that like if the determinant is not equals to 0, then you can say that it does have an inverse.
Exactly.
Yeah, so can we just state that for 5b?
So 5b, yeah, that's essentially what we're doing. We're finding that the determinant is not equal to 0, and therefore it has an inverse, and it's in GL 2Q.
Okay, and we don't have to find the inverse, right? Just
Yeah, this
where,
is not asking you to find the inverse. It's just asking you to find the inverse for C.
okay, thank you.
Yeah, no problem. So we have 1, 2, 3, 4, and in this case, we would. It's actually not asking. It's telling us that this is in the group, but it's good to check it. So the determinant of this is going to be equal to 1, 4, 2. So that's 4 minus 6 is equal to -2 is equal to 5 mod 7, right? Cool. So what is our normal way for finding the determinant of a 2 by 2?
Normally take 1 over the determinant and multiply it by the matrix, where you switch A and B and negative.
You drifted off there.
You take 1 over the determinant.
So are you saying the 1 over the determinant of what is it? It's A D C B, right?
Yeah. You crap.
Is that the correct form there?
Switch A and D and make C and B negative.
There's a minus somewhere. Okay. Determinant of a 2 by 2
Minus C and B.
minus C and B. Okay. Thank you. I don't have that method memorized because I usually just for the 2 by 2 stick with the A B C D 1 0 0 1, and then do the row reductions, which
Um,
I'll do that in a minute, but I'll just plug it in first.
I'm sorry, the inverse it's A and then the B and C, you don't flip them. They stay where it is, but just the negative.
Okay, so this is negative B, this is negative C.
Yes.
Okay, cool. So what is negative B? What is -2 mod 7?
5.
Yeah, so we get 5. And then we keep 1 and 4, right? And then what is -3 mod 7? What is -3 mod 7?
Where?
Yeah, 4, exactly. Cool. And then we're still dividing by 5, right? But what does dividing by 5 mean? So that's the equivalent of saying we're multiplying by 5 inverse. What is 5 inverse in this setting? In other words, what do I multiply by 5? So 5 inverse is equal to A. A times 5 is equal to 1 mod 7.
3.
Exactly. So if we do 3 times 5, we get that's equal to 15 is equal to 1 mod 7, right? So this is equivalent to 3 times this. So I get 1, 5, 4, 4. So we would get 3, then we get 1, and then we would get 5, 5. Cool. there's a few other. So first off, I encourage you to yeah. So the idea that the fraction is just our normal sense of inverse, but that we can actually generalize that is one of the important insights of this class. The idea of kind of a lot of the idea in algebra is kind of the generalization of things that you're familiar with from some settings to other settings. Why not? Okay. And I strongly encourage you guys multiply this guy times this guy to check that you actually get the identity matrix. But let's see what we would get if we did this method. So if we did this method, we would get 1, 4, 1, 2, 3, 4, 1, 0, 0, 1. So what am I going to do? I'm going to take, I'm going to do R2 is equal to R2 minus 3R1, right? Because I want to make this equal to 0. So that gives me, that's 1, 2, and this becomes 0 by design, and then I get 4 minus 6. So that's -2 is 5, right? One, and then I have minus 3, so that's 4, right? 0, 1. And now I'm going to have to get rid of this 5. So what am I going to do? I'm just going to multiply. So R2 is equal to 3R2. So that gives me 1, 2, 0, 1. And then I get 1, 0. And then here, if I multiply this by 3, I get 5. And then if I multiply this by 3, I get 3. So then so this guy right here, that's 1. So I do R1 is equal to R1 minus 2R2, right? So that would give me 1, 0, 0, 1, and then I would get 1. So then I would get -6, which is the same thing as 1, 5, 3. So these two methods seem to be giving different answers. That probably just means that I made a computational mistake at some point. They should both generalize perfectly fine to matrix multiplication over other fields. You guys haven't talked about fields, but they're an extension of the idea of groups to having two different operations. So run through, check my arithmetic. I probably made a mistake somewhere. And then the easiest way to check it will be actually just to multiply this matrix and this matrix by this and to see what the actual answer is. Do people have a next question that they want me to go over?
Yeah, I just have a general question about the notation. So for problem 7, the product of the elements of the group, and I'm not sure if that means multiplying them together under the regular multiplication, or we just apply the group operation to all the elements. Because it makes sense to use the group operation, right?
Yeah, it is the group operation because you're not actually, you don't know that regular multiplication is defined.
Right.
Mm.
Yeah. Okay. So if the operation is addition, we just add all of the elements together, right? And then we square the whole thing.
Yes. So the square just means basically do the same thing again.
Right. Okay. Yeah. That makes sense.
Yeah. So do people have a specific question that they want me to run through, or any more?
Can you just go over the number 7?
Yeah, sure. So, what does it mean for a group to be abelian?
They're commutable.
Yeah, you're commutative. So if we have G is equal to the product of GI, so here, and then we have G squared is equal to the product GI, GI, right? So the core here is for all GI in G, right? GI inverse is equal to GI, or GI inverse is equal to GJ, J not equal to I, right? Does that make sense? Do you grok that?
Yeah.
Cool. So in this case, so let's reorganize this. Let's break this up into the two different sets. So G squared is equal to the product of, we'll call this set self-inverses, and this is different inverses. So we get the product of GI over self-inverses times the product GI over different inverses. What is this right here? What is this right here? What is GI? Yes. This is just this right here. Each of these is E. So you just have the product of identities. The product of identities is just identities. So this whole thing is just the identity. And then these guys, well, every single one of these is, we can just pair it up with the GJ that is also in the different inverses, right? Because if GI is in different inverses, so is GJ. So this guy right here is going to be, we can rewrite that as GI, GJ, GI, GJ for the product over pairs of inverses. And that is just going to be equal to the identity again. Does that make sense to people? Do we need to go into so much detail, or can we just acknowledge that each element in G has unique inverse and that the inverse? Yeah, that's fine. That's perfectly fine. I'm just trying to give you guys the intuition. In fact, this is not really that clean of a proof. How you described is probably a better proof. Part of this is to just kind of give you guys a broader intuition for what's happening in these things. Cool. And the reason that, or part of the reason I also went into this detail is because if there are elements that are self-inverses, then that's the thing that makes us require this G squared. If nothing is a self-inverse, then we can actually just get away with just G being the infolution. But the second we introduce one of those, we're not guaranteed that anymore. There are still cases where everything is a self-inverse, and we would not get that. And the classic example of that is the Klein 4 group. So to give you guys the Cayley table there, we E, A, B, C, A, B, C, E, 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 E. So A, B, C, A, B, C. Have you guys done the Klein 4 group yet?
Yeah.
You did? Cool. So then this is a bit redundant, but B, C, so that's A, cool. So this is a bit redundant, but this is a group where everything is its own inverse, but I can pair A plus B is going to be equal to C, so A plus B plus C is going to get me back to E. Does that make sense? Cool. Any other questions people want me to go over? So, can I go over 1? That seems like a pretty good place to start. So let G be a finite group and A be an element of G that is not the identity. Let H equal AX for all X in G. Prove that H is equal to G. Okay, so the core intuition here is that if A is a group, then if A is an element, so that is not the identity is actually not relevant. It's not particularly interesting if A happens to be the identity. Obviously, then it's going to be the identity. But so if we have A is equal, or we have a finite group. A composed with G is going to be equal to A, so G1, G2, if and only if G1 is equal to G2, right? So this is the core intuition that is going to underlie this proof. Does this make sense?
Yes.
Do people see why, if this is true, then we would get the rest? Why it would follow that H would be equal to G? Has to do with it being finite. So if every single element is going to give us something else here, right? Then is going to give us a different element of G, because it's closed under under whatever our operation is. Then just by pigeonhole principle, if their H is going to be a subset or a subgroup of G and it has the same size as G, then H has to be equal to G. So that's the basic intuition underlying this. Do you want me to is that enough, or do you want me to actually go through and prove this? We have a few more minutes, so I'm fine with either that or trying to provide the intuition for another problem. Somebody give me an answer. Anyone? Hello? Prove it. Cool. So what do we know about this group G? We just basically just know that it is finite, and we're taking any element A in G and applying it to every single element in G, right? So we get A, G2, A, G2 is going to be equal to G3. So where do I want to go with this? So actually, I'm just going to try to prove that if AG1 is equal to AG2, then then G1 is equal to G2. So if I prove this, then I've proven most of it. How do you think I want to go around? How do you think I want to go about proving this? It's pretty simple.
Use the law of cancellation.
Yeah, exactly. I just multiply by A inverse, right? So I just to prove this, multiply, left multiply by A inverse. So then what does that tell me? That tells me that AX for all X, that tells me that the cardinality of H is going to be equal to the cardinality of G, because AX will produce a distinct element of H. Come on, for each element of G. By closure of star, H is a subset of G. And if two finite sets have the same number of elements, and one is a subset of the other, then they are equal. Therefore, H is equal to G. Cool. Does anyone have any other quick questions that they want to ask before I call this? I will take that as a no. Have a good day.
Thank you.
Thank